Okay, this lecture will just be on action potentials that occur in the heart. You've already learned about action potentials that occur in skeletal muscle and along skeletal muscle fibers and any muscle fiber, and then also along neurons. But the cardiac muscle, when an action potential travels along the plasma membrane of a cardiac muscle, it's going to be a little different. And so we have to review skeletal muscle and neuron action potential conduction, and then we will go into cardiac action potentials. First of all, before we even get there, remember that if you're a skeletal muscle, that any muscle, you're going to contract, etc., you've got a motor neuron going out to the muscle to actually send an action potential there, and then you have everything that happens at the neuromuscular junction to start the action potential on the skeletal muscle cell. So a skeletal muscle cell is not going to contract unless it is innervated. There is always going to be a motor neuron that's going to stimulate each individual muscle fiber that contracts, meaning if there are 5 muscle cells right here, long and cylindrical, if only one of them is innervated and an action potential goes down it, only one contracts. That is very different than cardiac muscle. Also, we have these things called motor units. If you'll remember the definition for a motor unit, it is a motor neuron and all of the skeletal muscles cells that it recruits. And so there's a picture on the next page. I'm not even going to try to draw that. But when a motor neuron sends an action potential down it, if it stimulates 15 skeletal muscle cells, then all 15 of those cells will contract. But you know, each skeletal muscle is made of many more cells than just 15. And so we have many motor units in each, well, it depends. We have more than one motor unit in each skeletal muscle. And then that way we can recruit more motor units, meaning we can vary the strength of our contractions. If I'm going to lift something very light, then I need a weak contraction and maybe only one motor unit will be recruited. If I'm trying to lift something slightly heavier, say, let's go from the pen to, say, a cell phone, and I'm just trying to hold it here, then we're going to recruit more motor units. In other words, maybe 2 neurons in all the skeletal muscle cells that they innervate. Those guys are going to contract. And if we want the strongest muscle contraction, so you're going to try to lift your car, you want every single skeletal muscle fiber to contract, then you recruit every motor unit. So please look up that definition of a motor unit again, and you'll see it on the next slide. Here is a very important point. The action potentials that occur on skeletal muscles, they have something called an absolute refractory period. And this is a time when you cannot, forget about it, cannot stimulate the cell. There's a time where, and that ensures that each skeletal muscle, well, I can't say that about skeletal muscle, but each action potential is separated from the others. They never merge. There is this period, and I'll show you on a graph, and it's only 1 to 2 milliseconds long compared to how long an actual muscle cell contraction is, which could be up to 100 milliseconds. Let's go over here to the cardiac muscle and compare a skeletal muscle. Because the cardiac cells, let's see, I can't go back because I've annotated this already, but because each of the skeletal muscle cells are connected to one another at intercalated disc, here we go, right here, and those intercalated disc, add my striations. At that intercalated disc, we have gap junctions and adhering junctions to make sure they don't pull apart, but the gap junctions are for communication. And because all the cells are connected, this cell, if it contracts, then this cell will contract, and every cell that they contract to every cell that they're connected to by gap junctions, I'm having trouble. Am I having a stroke? Probably just need water. Okay, anyway, if one cell contracts, they all contract, and we call that a functional syncytium. That's not like with skeletal muscle cells. If you have 100 skeletal muscle cells and they're all like touching each other, they're not really, because they have that outer loose connective tissue that wraps around each individual skeletal muscle fiber. So that's a big difference there. If one cell contracts, they all contract when it comes to heart muscle. There are some issues there, but we can make that generalization. Also, instead of a motor neuron coming out, like here's a motor neuron, believe it or not, is the bouton or the axonal terminal. And here's our skeletal muscle cell. And then we have that synaptic cleft. Oh, that's getting better and better every day with the drawings. Multinucleate. This is a skeletal muscle cell. This is the neuromuscular junction where the nervous system and the muscular system come together. Remember that we'll secrete, in the case of skeletal muscle, acetylcholine into the synaptic cleft, and then it creates the electricity that's going to go along this skeletal muscle. Well, if there's a skeletal muscle right here, muscle cell right here, that's not innervated by that neuron, it's not going to contract, even though they're right beside each other. Boy, I'm beating a dead horse. But anyway, here is the neuron. So we have the nervous system coming in, telling the skeletal muscle to contract. Now, the nervous system is going to modulate cardiac contractions, but we don't need the nervous system. You could literally yank somebody's heart out of their chest. I mean, you can't really, but pretend like you did. It will still beat without the nervous system innervating it. So we have these things called autorhythmic cells. They're self-excitable, meaning they're not cardiac cells. They're not myocytes. They're not going to contract, but they're a little cell that's unstable and it just fires off. It's in the heart. We're going to learn about the pacemaker in a different lecture, but they just fire off action potentials. And so if they fire off 50 action potentials per minute, your heart rate is 50 heartbeats per minute. So they excite the cardiac cells. So maybe I have a group of cells right here that they just fire off action potentials in every direction. Well, if the action potential stimulates this cell, because the cardiac muscle acts as a functional syncytium, then all the cells will contract, which is pretty crazy cool. Now, here also, I put 2 stars over here. How about 4 over here? This is an incredibly important point. Your heart is a pump, and it's pumping away. And it's pumping blood through your arteries and your veins, a closed circulatory system. We don't want it open inside because then we could not maintain blood pressure. But one thing to maintain blood pressure? Well, your heart's just pumping and sending that blood around the body, correct? We don't want the heart to go like this and then just stop contracting. Because if it stops contracting, it's not sending blood anywhere. Now, then you will die. So we have to have, in the action potential that's going along the cardiac myocytes, we have to have an extremely long refractory period. Here we have a very short one. So if we were to, an action potential is going to look like this. If we shorten what an action potential looks like to this, then the next one could happen, and the next one, and the next one. I'm really bad at illustrating. But when it comes to this muscle over here, instead of our action potential looking like this, we're going to have something that looks like this. Oh, it's looking the same already. But then we have this plateau, and then it goes out. So we're still going to have the depolarization phase, as we've had in skeletal muscle and nervous tissue. And we're going to have the repolarization phase, but we have this really cool thing called a plateau. And if you've never been on a plateau, you should go try to find one. It's kind of interesting. But this is a plateau on a graph. And let's see if I can get rid of all this stuff and move forward. Anybody have any questions? Just kidding. Okay. Now, here we go again. This is contrasting the skeletal muscle and the cardiac muscle. Here we have just one neuron. This is a motor neuron, and these are the axon terminals coming out, and they're innervating these cells. This is a motor unit, the motor neuron plus the skeletal muscle fibers that it innervates. It's innervating this guy right here. This is a skeletal muscle cell. See it going all the way this way long? It's innervating this guy. These little things inside of it are the myofibrils. So all the way this way, that's a skeletal muscle cell. Remember, they're long and they're cylindrical, right? And then this guy is innervating this little axonal terminal or bouton is coming out, innervating this guy, and this one's innervating this, and it looks like this cell has branched. And so if an action potential, which is the electricity of the neurons, goes down to the very end of the boutons to the neuromuscular junction, it's only going to stimulate out of this whole bundle of cells. It's only going to stimulate the cells that it innervates. 1, 2, 3, 4, 5, 6. These guys are not going to contract because they're not part of the motor unit. And that's how we have graded responses to the varying strengths of muscle contractions that we need. When it comes to the heart muscle, the functional syncytium, because they're all connected together, and these gap junctions are the important thing in this case. The desmosomes prevent the heart cells from being ripped apart. The gap junctions, if one cell does something, another cell does it because the connective tissue, the cytoplasm of both cells are connected. So we get this functional syncytium. One cell contracts, they all contract. Look at that, smooth like butter, 15 clicks. Okay, here, I know you all love this because we've done this repeatedly in the first semester of the class, actual action potentials of muscle cells, skeletal muscle in particular, and nervous tissue. Now, we always use -70 millivolts as our average down here, like they did over here. And this is threshold. This is that point at which that once you reach this threshold point, an action potential is going to occur. And so these two graphs, this one and this one, are the same thing, but they're illustrating two different things. So let's go over the first one. Remember, in skeletal muscle or in a neuron, when you have an action potential flowing on them, you have this part right here. We're at resting membrane potential, where we have potential to do work, but we're just at rest. The inside of the cell is negatively charged, positively on the outside. We have more sodium outside of the cell. This is the outside. This is the inside down here. We have more potassium on the inside, and that's maintained by the sodium-potassium pump, maintaining this equilibrium. So that's at rest. But what happens when you get a stimulus, and the stimulus would occur right here, sodium gates are going to open. We have those fast voltage regulated sodium gates. So they all open. Well, they open first. And when they open, because we have more sodium on the outside of the cell, when we're here in this depolarization phase, the potassium's on the inside and the sodium comes into the cell. So that flip-flops the charges and we're depolarizing the membrane, meaning we're going away from negative. We start off with, say, -70 millivolts, -55 is depolarized because this is more positive or less negative. And we go all the way up to +20. I've always used +30, just makes it easier to be consistent for me. But during this phase of depolarization, we have sodium rushing into the cell because the sodium gates are open. So, and during depolarization, sodium's rushing in because the sodium gates are open. Then those sodium gates close. And then potassium gates open. And the reason the potassium gates open second is because these guys are fast voltage regulated gates, the sodium. So you zap the sodium and the potassium gates at the same time, and the sodium are like, up, up. And then the potassium are like, whoa, and then they open up and then they close. So potassium gates are stimulated at the same time as the sodium gates. They're just more sluggish, right? And so you open those potassium gates, and this is during depolarization down here. And during repolarization, what we're doing is we're driving that membrane back to its resting membrane potential. We're making it become more negative on the inside. So to do that, we've got the sodium trapped in here and the potassium exits. And so that repolarizes the membrane and makes us more negative on the inside. But now our potassium's on the outside of the cell and the sodium's on the inside. We don't want that. We do want it negative on the inside to get our cell back at rest. And we do want it positive on the outside. But what we want for resting membrane potential is this. What we have at this very moment, Of course, I won't be able to erase. Is negative on the inside of the cell, positive on the outside, but our ions are in the wrong place. Notice down here, sodium here, potassium. So now we have sodium on the inside and potassium on the outside. So, by the way, this dips down a little bit more, lower than resting membrane potential. That's hyperpolarizing the membrane, if you will recall. To get us back to total normal resting membrane potential again, we need that sodium-potassium pump to pump this sodium out and this potassium in to return us to that normal state of rest. Okay, that's our action potential review for skeletal muscle cells and for neurons. But when it comes to this guy over here, you see this is still an action potential, but what it's highlighting in blue and purple here, this is all, believe it or not, purple. This is our absolute refractory period. It's a very short amount of time. How I like to think about it is this. Well, this is the absolute refractory period is you can't stimulate the cell. You can't stimulate the cell. Absolutely, you cannot stimulate the cell. It's already stimulated. When we get to the relative refractory period, that's when I wish the artist would have drawn this even with resting membrane potential. But that's this undershoot here where we go below -70, maybe down to 80 millivolts. That hyperpolarizes the membrane and it makes the cell, it makes it harder for the cell to respond to a stimulus. So the cell can respond, but it has to be an exceptionally strong stimulus. So that's why it's called the relative refractory period. What we want to focus on for this chapter is the absolute refractory period. Look how small it is. The cell can't possibly be stimulated. How I like to imagine it is if you open every door in your house, can you open any more doors? No, you just can't do it. All the doors are open, right? Well, if you open all the sodium gates and the sodium's rushing in and you apply a stimulus, if all the gates are open, you can't open any more gates. You just can't stimulate the cell. So keep this in mind. Look how short that absolute refractory period is. It is only like 1 to 2 milliseconds. Because now we're going to go and we're going to start on the cardiac action potential. Here's what a cardiac action potential looks. See this gap right here? Look, that beautiful word, the plateau. There's the plateau. During this part, we are going to have, they've not put the threshold in here, but we are going to have depolarization phase. So here, those fast sodium gates open, sodium rushes in, and that causes depolarization. And then on this side, it's going to be the same old story. Finally, the potassium gates open, potassium rushes out, and that repolarizes the membrane, takes it back. But up here, we have this really neat flat plateau, like I drew it before, like this. And this plateau phase is due to calcium gates. They're voltage regulated calcium gates. This one's the fastest, this one's the second fastest, this one's the third fastest. That's why they're opening in the order in which they're opening. But that voltage regulated calcium gates, when they open, calcium rushes in. So it maintains, here we've depolarized the cell, and now this calcium rushing in keeps us in the positive here, and it keeps us depolarized for a long time. And you'll notice they cut a little gap in here because it would be too long to draw between 2 milliseconds and say 400 milliseconds. That's a long time to be in this, what they've colored here. That is the absolute refractory period. So what that means is an action potential is going to go across the cardiac muscle cell. And then there's going to be a long period of time in milliseconds. I mean, that's not long, but there's going to be enough time to make sure that each heart, no matter how fast your heart is beating, it's going to be separate because of these prolonged plateau phases in the action potential. And so it prevents our heart from going into tetany. Look the word tetany up, not tetanus, just regular tetany of skeletal muscles, and just enjoy the fact that your heart beats instead of locks up. We don't want it to lock up because then you die. Let's see what's next. Aha, this is just the same thing that I've said over and over because I like to beat a dead horse. The skeletal muscle, it's going to be depolarized by fast over here on this side, going to be depolarized by those fast sodium gates that open, and then sodium gates close and potassium gates open. It's going to be repolarized by potassium gates opening. So here we have sodium rushing into the cell. Here we have potassium rushing out. And then we have the sodium potassium pump fixing everything. Things that you know, like you talk about at the breakfast table. When we get to cardiac muscle, here on this side, we still have the sodium rushing in. We still have the potassium over here rushing out. So it's the same story, depolarization and repolarization, but we have a continued here, this plateau phase is continued because slow voltage regulated. I was wondering if my notes were wrong. Here we have the potassium, the calcium coming in because the calcium opened up after the sodium gates. Saying the same thing over and over. It's an eventual brainwash. Oh, look, same thing again. But this time I'm going to really say the absolute refractory period. It's important. It's important. Here it's in skeletal muscle or in neurons. This is the absolute refractory period as I see it over here. What are they doing here? Yeah, the absolute refractory period. Let's put it all the way through there, but it's short. Over here, look how long this refractory period is, and that is due to the calcium, the plateau phase of the actual action potential. Okay, we'll get to the cardiac conduction system. This is going to be a lecture on the autorhythmic cells in the next lecture.